Thank you, Wes. So to those who don't know me, my name is Adi Rozenberg. As Wes introduced me, I'm the CTO of AlvaLinks. And today I'm going to talk about RIST specification and multicast workflow. It will going to be an historical review of how RIST and multicast coexist and why we believe that there's a necessity to preserve the old multicast workflows that are running in the old plants and new plants and running to the cloud and so on. So let's start with the beginning. From its inception in 2017, one of the key requirements was to preserve the traditional workflow of the multicast delivery. Why did we use multicast in the past or today? Is because it's very easy to move multicast. You don't need to set too much in your system. You have an encoder, you set an IP address with the multicast and a port. You have a receiver with the same. And all you need is a multicast-enabled network, and it just works. And because it just works, that is why people find it very easy to debug, to maintain, and to preserve that. So we saw the need to preserve that as much as we can. Multicast original packet preservation, which is the IP header, payload, and timing, are key for customer troubleshooting and satisfaction. By preserving source to destination packets, we can identify and isolate source transport or destination problems. Standard internet does not allow multicasting, and that is very unfortunate. This is why we have to use a tunnel or a VPN to allow multicasting between on-prem, the cloud, or you go and buy yourself a multicast-enabled network, and some people do that. All RIST technical recommendations sought out to preserve this requirement. I'm talking about the simple profile, main profile, advanced profile, and even the new auxiliary profiles, parts 2, 3, and 5, which I'm not going to talk about. And let's start with a simple profile. And just to explain, simple profile used today by AWS Media Connect, for example. The simple profile allows the use of multicast streaming and providing an ARQ level between a RIST sender and a RIST receiver. Error corrections can be applied using SMPTE 2022-1 and 2, ARQ, and the use of SMPTE 2022-7 with a multipath, so that you have sometimes faster recovery or better results and resilience. SMPTE 2022-1 FAC packet is sent to one or more receiver using the multicast. ARQ retransmissions can be sent to as a multicast to all, or to use a unicast to receivers that need that recovery. That is selectable by the user. The multicast can be delivered as a duplicate or over multiple paths or with load balancing across multiple paths. And we demonstrated that in the RIST activity group and multiple demos doing exactly that with a simple profile. So let's see that simple profile multicast streaming. You can see here a RIST on top RIST sender using a LAN, sending to a RIST taker. We can do the same with a RIST simple profile, sending that over LAN, MPLS, or a VPN. So that might be an MPLS link to the cloud, an MPLS over a WAN barrier. If you want extra security over a network, you will use a VPN, for example, WireGuard, IPSec, GRE. All of those support multicasting natively, so you can move simple profile and preserve the flow. And here we see also example the use of SMPTE 2022-7. Seamless or hitless failover. The idea is that we can use multiple paths to send duplicate copies over multiple different networks. We can bond 5G, 4G, LAN, WAN, whatever, to bring that to the RIST receiver, and it will re-aggregate the stream back to its original form. By preserving the multicast, we create less changes in the IP packet. Less processing, we just forward that, and at the end, we just buffer that to get rid of jitter and to allow us to do error recovery. And then we output that unchanged outwards. Now we are going to the RIST main profile and multicast. The RIST main profile basically gives us the ability to create a tunnel, a GRE over UDP tunnel that encapsulates that simple profile that we saw before. Now we can move, it's moving a multicast inside the unicast flow from one point to others. You can create a point to multi-point and carry that multicast over to the destination, to the cloud, or even I have used it many times in the cloud itself using main profile to run between availability zones at the times that AWS, for example, didn't have multicast support. So using a RIST tunnel, I was able to carry that multicast easily. It's very traceable, and I don't need much experience to do that. Another example or use case that we envisioned is the use of, if we are going to do satellite replacement, we want to have the same notion of multicasting. So if we have a multicast-enabled network in an internet, on a segment, why not to send multicast? But then the question was, what about security while doing so? How do we protect the content, just like we did with satellite? For that, the RIST activity group added PSK encryption. So now we can send multicast and encrypt that multicast and send it over a multicast-enabled network. So it is running, the GRE over UDP packet is running multicast, and inside you run a multicast. So, and everything else is, encapsulated with the PSK encryption. So let's see some images of that. So this is an example of a RIST tunnel. And in this example, we have sender, receiver at both ends. And this is a tunnel. We just push the multicast through the tunnel, and it reappears on the other end. ARQ is performed by simple profile. We can do FAC. We can do ARQ. We can do 702022-7. Very simple. The RIST main profile adds just the layer of encapsulation, the tunneling, the encryption, authentication on top of the original multicast. And hey, we can use the same tunnel for both directions. So suddenly we don't need to add another tunnel. We can, but we can use the same one to send the content through the tunnel. So once again, multicast can be received, sent, looped, and also we can send auxiliary data like TCP, KVM, whatever, through that RIST tunnel between the two locations. This is the point to multi-point distribution option. We send a multicast with PSK. So the IP address is in fact a multicast, and it is encrypted with PSK. And the use case for that is for satellite replacement or ABR multicast ABR, where you want to use a multicast, and here we adhere to that with this implementation. Another example of sending a multicast to multiple sites. And if we want to do ARQ, each one is handled individually, or we can send 2022-102 FAC packets on each tunnel to the receiver, so they are not tied together. So now we had a request from the market. The request came and said, wait a second, we are sending a multicast over the internet. Maybe somebody who is not allowed to consume that, a rogue agent, might come in and pick up on that multicast. And if by any chance he knows the PSK encryption, it will be easy for him to tap and see that. We took that challenge head on and we added multicast authentication. This is the first time that something like that was introduced to the industry. This is basically similar to a DRM type of an application. Each client is authenticated against the original server using a standard EAP SRP protocol, which is standard RFC. So now we know who is allowed to consume the content. We can also decide to drop receivers if we don't want them to receive because we identify them as a rogue agent. And once again, the RIST activity group rose to the challenge, and we were able to provide this capability for multicasting and so on. The next thing that the RIST activity did was the RIST Advanced Profile. So first, let's explain what is a RIST Advanced Profile to those who are not familiar with that. The RIST Advanced Profile is a new way of, it's a self-healing tunnel. We basically said, instead of doing RIST Simple Profile inside the tunnel, we will just push data through. The tunnel will take care of the error recovery. The tunnel will be very smart to react to the network condition without the user doing anything. So all you need to do is to use an advanced tunnel. It will do forward error correction. It will do 70-20-22-7. It will do load balancing, path diversity, all of those goodies without the user even knowing about it. In fact, you can multiplex multiple flows and give them an ID, and you can prioritize things through the tunnel, and the tunnel will be self-healing. So now multicast can only run inside the tunnel at either direction. So let's see how it works. And I forgot to mention the RIST Advanced Profile also support WireGuard VPN, which is a VPN available in most of the new OSs, operating systems, at the kernel level. And it gives a very good performance to those who don't want to code a full-blown advanced profile tunnel. They can use a WireGuard VPN that also support multicast. So we have the same performance. It's once again, self-healing. You don't need to do anything. Just push multicast in. Multicast will come out. Easy breezy. It's perfect for the cloud. The perfect intercloud, hybrid, on-prem work. Everything perfectly suited for many use cases. Unfortunately, the RIST activity group did not stop into that. So we added a new functionality, a RIST relay. And what is the RIST relay and how it does work with the multicast? The RIST relay is a point in the cloud that sits outside your organization, and it proxies the data, the tunneling for you. So its first priority is to overcome firewall challenges, just like Skype will do. You basically go through a proxy server, or what we call a relay server. That relay server can also be very friendly for multicast. You can send one multicast to that relay server, and it can duplicate and distribute the multicast to the destinations. It can also do the opposite. It can take multicast from multiple sources and remultiplex them to one organization or multiple. You can create groups of people that tune to a multicast. Just like you will do with Zoom, Teams, you can create like a joint call or what of many users that will tune to the same multicast. And because it's an using an advanced profile, it can be delivered over GRE and WireGuard. So the example for that, we have a very known content as a playout. It goes to a RIST relay, and the RIST relay now distribute that to the decoders. You basically command the relay, I want you to send the data to those receivers. And once again, the multicast workflow is preserved. You don't need to do do anything. Next, there was a request from a vendor, and he came up with a challenge. I want to preserve the the old way we used to do multicasting and have IGMP capability. I don't want you to send me data, a multicast data, if I haven't joined that data. And another application that, like for IPTV for hotels, if nobody is asking to consume the data, to watch, to consume a specific multicast, please don't send it to me anymore. So in fact, we are saving resources, less streaming to places that decided to stop receiving. So that is the RIST multicast discovery. We bring back the old IGMP capability by basically querying. Each endpoint queries the next one, what multicast he wants to consume or does not want to consume anymore. And if he doesn't, or he doesn't have a layer behind it, we will drop that multicast until the point that they will ask to join again the multicast, and we will send that to them. So imagine, for instance, we have an event with 200 cameras. Each camera has a multicast, but we want to consume only 5 of those at a remote destination. Why would we send 200 multicast streams if nobody consumes them? The 5 will join the multicast that they want to see. Those multicasts will be sent to them. They want to switch to another one, they will do an IGMP join. A new one will be sent to them, the old one will be removed. So we are saving bandwidth, we are doing much more efficient workflow. So this is how it seems. So, and by the way, RIST multicast discovery appears in all profiles. So it's not limited. So in this case, we have a sender. We are sending multicast. We can see IGMP query, basic queries, the levels after him. Each level also queries the taker. So if this is an hotel that we are sending ESPN, CNN, MSNBC, TNT, if nobody consumes a specific stream, don't bring it to us. If somebody wants to see that, we will issue a join. In a split of a second, that join will be sent to the next level and beyond, and the data will start streaming to us. And we are not wasting bandwidth, resources, power, and so on. So it's a very smart way of consuming bandwidth and not putting pressure on the network. This is an example, just to visualize that. The taker doesn't want to consume the data anymore. It issues an IGMP leave. We stop the stream. Now on this side, a taker was dropped, but we have other takers that still consume that content. So we continue to work as before. And here a taker joined and he wants to consume ESPN as an example. So the querier will discover that, will issue an IGMP join that will trickle to the sender, and a stream will be sent to it. Very efficient, preserving the traditional multicast workflow. And I am done. Any questions?